Hello, ladies and gentlemen, and welcome back. In this video, we're looking at question number 4. This is the last question on our 2019 Fryer contest. A Schonk sequence is a sequence of positive integers, and then we've got two conditions. Each term after the first is greater than the previous term, so it's an increasing sequence. And then the second condition, the product of all the terms is a perfect square. And we've got an example here. 2, 6, 27 is a Schonk sequence because 6 is bigger than 2 and 27 is bigger than 6. And 2 times 6 is 12 times 27 is 324, which is a perfect square. It's 18 squared. Okay. So we've got 2 light bulbs and 2 writtens. A part. If 12x24 is a Schonk sequence, what's the value of x? So basically, did you read and understand these two parts? This should be 2 easy marks for us. So the terms need to increase. So I need x to be between 12 and 24. Now 12 times 24, that's 24 is 2 times 12, so we get 2 times 12 squared. 2 times 144 is 288. Which I guess I'll write as 2 times 12 squared. So to make 12, you know what, I probably should put a dot up here so we don't get confused with the x. To make 12 times x times 24 a perfect square, what do we need? Well, we've already got 12 squared. That's a nice factor. Perfect squares are just perfect squares multiplied by more perfect squares. So we need x is 2 times a perfect square. Because then this 2 will pair up with this spare 2, and we'll get 2 squared. We already have 12 squared, and then k squared, and we'll be all set. I suppose I should write it maybe as a full square, 24k squared. That's what we'll end up getting. Okay, so can I find a number that works like that? Well, k could be 1, in which case you got 2 times 1 squared. Well, that's too small. 2 times 2 squared would be 8. That's too small. 2 times 3 squared is 2 times 9, which is 18, and that sits right in there. And the next one would be 2 times 4 squared. That would be 32. That's way too big. So I think we can see sort of by inspection, x equals 18 will do. And in fact, it's the only thing that will do. Okay. But, I mean, they say what's the value of x, so it's not like it was up for grabs that it could be more x's. There could be multiple ones that work. All right, B part. Again, it looks like we're just sort of exploring the definition of a Schonk sequence. If 28yz65 is a Schonk sequence, what are the values of y and z? Okay, again, we just sort of need to know what are these two values. It's a light bulb question, so we can just put our answer there. What have we already got? So 28 needs to be less than y, less than z, less than 65. So that limits the range of values for y and z. 28 times 65, that's 2 squared times 7 times 5 times 13. So yz needs to be, we need to have an extra factor of 7, an extra factor of 5, an extra factor of 13, and then any other square will do. Okay, we've already got 2 squared. The 2's sort of paired up, but I need something to pair up with this 7, this 5, and I need an extra 13 to pair up with this one, so we can get a factor of 13 squared. Okay. So 7, 5, and 13, these are prime numbers. Right? So I know 5 has to divide yz, but then because 5 is prime, either 5 divides y or 5 divides z, or maybe both. Okay, this is a nice general property of prime numbers. If a prime number divides a product, then that prime divides one of the two factors of the product, or one of the factors of the product. Okay? This is, for example, not true of something that isn't prime. So 6 divides 3 times 4, but 6 doesn't divide 4, and 6 doesn't divide 3. But with primes, you do get this nice split. All right, now I like the 13s here because, well, one of y or z has to be a multiple of 13, and there's only going to be so many multiples of 13 in this range. I mean, 65 is a multiple of 13. 52 is the one before that, and 39 is the one before that, but 26 is before that. So one of them, y or z, is either 39 or 52. Okay. Now, neither of these, so we'll say it, I'll write it down below. Neither of these is a multiple of 5 or 7. Okay, so that means I don't have 7 times 13, like y isn't 7 times 13 or anything like that. So, since I only have 2 numbers, that means 5 times 7 must be a factor of y or z, one of the two. We're not dealing with which numbers are bigger. But of course, that's 35. And how many multiples of 35 are between 28 and 65? Only one of them. Okay. Now I can see, well, 35 is less than both of my possible multiples of 13. So we see y has to be 35, and z is either 39 or 52. Now, which one is it? Well, if it were 39, you'd have 3 times 13. If it were 52, you'd have 4 times 13. If I pick z is 39, yes, I get the factor of 13, which pairs up with this factor of 13, and of course the 5 and the 7 are paired up with the 35. But I would introduce this 3, and I don't have an extra 3 lying around to pair up with anything. Whereas if I choose z is 52, the 13 pairs with the factor of 13 we already had, and then we get a 4, which is already a perfect square. So we see y's got to be 35, z will have to be 52, and those are the only solutions. Okay. So we would put them in the box provided in the booklet, and off we go to C part. All right, C, determine the length of the longest Schonk sequence, okay, each of whose terms is an integer between 1 and 12 inclusive. So my solution should include an example of a sequence this long, as well as explaining why no longer sequence is possible. Okay. Well, the best we could do is if 1, 2, 3, all the way up to 12 was a Schonk sequence. I'm going to suspect that it isn't, but let's find out. So 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12. We could bust out the calculator if we wanted to, but I think it might be easier to look at this with prime factors. I'm going to ignore the 1. Six becomes 2 times 3. 8 is 2 to the 3. 9 is 3 to the 2. A 2, a 5, an 11, and a 12 is 2 to the 3 times 3. Okay, so grouping this all together, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 7. Yeah, it looks like we get 2 to the 10. Okay, so we got 10 factors of 2 in here. Okay, and then how many factors of 3? 1, 2, 3, 4, 5. 5 factors of 3. 2 factors of 5. And then 1 factor of 7, 1 factor of 11, those are all the primes. Okay, so rather than looking for extra numbers to pair up with the 7 and 11, and you would need an extra 3 if you wanted to make a square, because you can tell if something's a square because if you write it as a prime factor, all the exponents are even. And we can see some of these exponents are not even. So we're not looking at a perfect square. So to make a perfect square, so we might say all exponents are not even, so not a perfect square. Okay, so to correct this, we need to get rid of a factor of 7, we need to get rid of a factor of 11, and we need to get rid of a factor of 3. Now we'd like to do that losing as few of these numbers as possible. For example, suppose we had an extra 2 kicking around. Okay, suppose we actually had an extra factor 2. We needed to get rid of a factor 2. We could remove 2 and 3 and 7 and 11 from our sequence, and that would remove 4 out of my 12 numbers. But if we were clever about it, we could say, well, you can get rid of a 2 and a 3 by getting rid of 6. Right? And that only removes 3 numbers. So we have to sort of be careful and think our way through it. Okay? But we don't. We do have 10 copies of 2 up here. So it looks like we need to lose one factor of 3, 7, and 11 each, because we've got enough. We've got an even number of 5s and even number of 2s. Now, unfortunately, there's no combinations, because 3 times 7 would be 21, 3 times 11 would be 33, 7 times 11, 77. We don't have these numbers in my sequence that I can drop. So to lose a factor of 7 and 11, we must remove 7 and 11 from our sequence. Okay. You've got to get, because they're the only sources of the 7 and 11. If we had 14 here, we'd have a choice. Which one do I get rid of to get rid of a factor of 7? But we don't have that choice anymore. Okay, so we get rid of the 7 and 11. This leaves the 3. We can get rid of a 3 by removing a 3, a 6, a 9, or a 12. We can't get rid of the 6, because that takes a 2 with it. You can't get rid of the 9, because that actually takes 2 3s. And then you'd still only have an odd number of 3s. You can get rid of the 3. You can also get rid of the 12. Okay? Because it's 2 squared times 3. Yeah, you'll lose 2 of the factors of 2, but we're not trying for the biggest square. We just want a square. And so if I get rid of the 3, but at the same time I lose 2 of the 2s, I'll still have an even number of 2s. I'll just only have 8 of them. Okay? So we're actually doing something a little bit better. The 2 longest chunk sequences possible are 1, 2, skip out on the 3, 4, 5, 6, skip out on the 7, 8, 9, 10, no 11s, and a 12. And then you could also leave the 3 in and get rid of the 12. And these have, what, 2, 4, 6, 8. 2, 4, 6, 8, oh, 9. backwards. Yeah, because we lost 3 numbers. 9 terms in both. Okay? Not only have I given the examples they asked for, I've explained my answer. It is 9 terms in both, and I've explained why you can't lose any more. You have to lose the 7 and 11. So already you're down to, at most, a length 10 sequence, but you do have to lose a factor of 3. And at worst, you would lose 1 number for that factor of 3. Okay. So there we go, on to D part. What have we got here? A sequence of 4 terms, A, B, C, D, is called a super-duper shonkolistic sequence. I'm sure they had fun making up these names. I didn't think Shonk is somebody's last name. Maybe it is. I don't think Shonk is somebody's last name. And I really suspect they're just having fun with words. Super-duper shonkolistic sequence. Alright, so it's called that. Exactly when each of the A, B, C, D, A, B, C, and B, C, D is a Shonk sequence. So when the whole thing is a Shonk sequence and when these smaller parts are Shonk sequences. Determine the number of pairs M and N so that this is a super-duper shonkolistic sequence. Okay. Well, I think just like in Part C, we probably want to look at prime factors. Now remember, since M, 136, N, and then it was 48 something? 48,400. So part of being a super-duper shonkolistic sequence is you've got to be a Shonk sequence. So M has to be less than 1,176, less than N, 48400. Okay. Now, M176N is a perfect square. Let's call it P squared. And then if we bring in, I think N will probably be the first thing to focus on. If we multiply all these, we'll get another perfect square. Maybe call it Q squared. Okay. Now, we also know that M176N 48400 is another perfect square. Maybe call it R squared. If I divide this by Q squared, I should get M. So M is a perfect square. Okay. Because it's one square divided by another square, so this is whatever R over Q is, all squared. And R over Q will have to be an integer, because when you square it, you get an integer that we know is M. It just so happens that M is a perfect square. Okay, what else can we see? Well, I'm going to say something like let M be S squared. Then I know P squared over S squared is P over S all squared, but it's also equal to M176N over M, which is 176N. So 176N is a perfect square. All right, I think we've been sort of avoiding the issue long enough. 1,176. What are you as a square? Obviously, you got a factor of 4 here. So I'm going to divide by 4. I'm just going to speed this up with my calculator. 1176 divided by 4. 294. That's definitely a multiple of 2, but not a multiple of 4. 147, is that... No, that's a multiple of 3. 3, and then we get 49. So 1176 is 2 to the 3, 3 to the 1, and 7 squared. So we conclude n is a multiple of 6. N's got to be a multiple of 6. Not only that, say in fact, n has to be 6 times another perfect square. I'm going to call it t squared. Okay, so m has to be a perfect square less than 1176. And n is 6 times a perfect square and sits in between these two values. Okay. And I think that should be it. Right? If that's the case, then s squared. So I'm going to say, I say this suffices. I claim this suffices. I claim is probably the better mathematical thing to say, isn't it? So I claim this suffices. So m176n would be s squared t squared, and then 1176 times 6, 756, and that would be something st squared. What is the square root of 7056? 84. So that'd be 84 squared. 1176 n 48400. I think this is 220 squared, but we'd get t squared, the 6, and the 1176 again combined. This will be t squared, 84, and then 48400 square root is 220. So multiply that by 84, and you'll have 18,480 t squared is that expression. And that's going to be the same thing, but with an s added in. So that would work. They would be Schonk sequences because as long as we get this order right. Okay, so we just need to... It looks like the m doesn't have any impact on the n, and that's nice. So, let's say... They've got to be positive integers, right? Positive integers. Schonk sequence positive integers. Okay. So, m, which is the same as s squared, is somewhere in this range because it has to be less than, strictly less than 1176. Square root both sides. Square root of that should be, oh, I don't know, something like 4 times 7, so square root 1175. So about 34.2. So s can be any value between 1 and 34. So we get 34 choices for what m is going to be. Okay? 34 choices for s, and then 34 choices for m, once you square them. So it goes all the way up to m possibly being 1156. Okay, so now we've got 1176 is less than 6t squared, which is the same as n, and it's got to be less than 48400. So I can divide this side by 6. (1176) divided by 6. So 196 less than t squared. So if we weren't careful, if we put an equal sign here, we might accidentally get t could be 14, which is not allowed. And then this is not a multiple of 6. So we'll get 197 is less than or equal to t squared, less than or equal to 8,066. And now I just square root both sides. All right, so that'll be 15 for your minimum value of t, because square root of 197 is just over 14. And then the square root of 8,066 is going to be just over, or just under 90. So at most t could be 89. Okay, so how many values of t does that give me? The values of t give me the values of n. So n can be any of, so I want to count these numbers inclusively. So take one, subtract the other, and add one. So that should be 75 values of n. Okay. If we wanted to, we could double check. 89 squared times 6 is less than 48400. But if I did 90 squared and I multiply it by 6, that's more. Same thing, 15 squared times 6, we're in the clear. Okay, so there are 75 choices there. Okay, so the possible pairs mn, number of pairs. M has nothing to do with n, they're completely separate, so we had 34 choices for m, 75 choices for n, and while we still got our calculator handy, we can work that out. So there's 2,550 possible super duper shunkleistic sequences. And there we go. Okay, a little exploration there at the end. I like that. I really like the name super duper shunkleistic sequences. I would have loved to be in the naming room for that, but oh well, there we go. Okay, so that's question number 4, all tucked away there. And that's it for our 2019 Friar. If you're looking for a harder contest in the same year, I would recommend the 2019 Galois paper. And if you're looking for other Friars, of course, feel free to explore the channel. Feel free to throw a like on the video if you liked the question, or feel free to subscribe as a way of showing support for the channel. But I leave all that up to you. You certainly don't feel any pressure to do that. And I'll see you for more math in the future. Until then, take care and have a wonderful day.